So if we look at this second example, it's a bit more difficult because we've got a different mole ratio now. We haven't got 1:1 mole ratio running through this. We've actually got 1:1 to 2 mole ratio. But we're going to just employ the same method, and hopefully you'll see that these calculations, even with mole ratios, aren't too bad. So first thing, initial moles. So we're told that 0.206 hydrogen, 206, and 0.144 of iodine. So there'll be none of this at the start. And then we'll leave some space for the change. We'll go to the E. Remember, this is the equilibrium moles. And we're told that at equilibrium, 0.258 moles of HI were present. So we'll know this amount now, 0.258. So, how have these changed? Well, if we look at that, 0.258 HI, well, they've come from these, and the mole ratio of H2 to HI is 1 to 2. So to produce that many moles of HI, half as many moles of H2 needs to react. So this is going to be 0.258 divided by 2. And again, to make 2 moles of HI, 1 mole of I2 is needed. So to make 0.258, we're going to lose this many. So those values you can see are coming out at 0.129 each. So just to confirm, to make 0.258 moles of HI, we need half as many moles of H2 and half as many moles as I2. So these are going to drop. This initial moles value will drop by this amount because it's making that. And so the difference between those two will be the equilibrium moles of hydrogen. So that's 0.077, and this one will be 0.144, just doing this on the calculator now, minus 0.129, which is coming out at 0.015. So we now have our equilibrium moles. The question's been nice in the sense that the volume of the container is 1 cubic decimeter, so the equilibrium concentrations, moles over volume, so it's that over 1, that over 1, that over 1, so they're just the same. So we can use the same numbers because effectively they are the concentrations. So we need to plug these values into the Kc expression. So there's the expression for Kc, equilibrium concentration of products, raised to the power 2 now, because we've got this balancing number here, divided by the equilibrium concentrations of the reactants, both to the power 1, because there's no number required to balance it. So we're feeding these equilibrium concentrations into the expression, 0.258 squared, divided by 0.077, multiplied by 0.015, and that comes out at 57.63. In terms of units, moles per decimeter cubed squared on the top, moles per decimeter cubed squared on the bottom. So again, there's another one with no units. We'll do one more of these. If you want to try this yourselves, pause and then obviously start playing again. I'll go through the answer. So we've got a mixture of 2 moles of CO and 5 moles of Cl2. They're allowed to reach equilibrium in a 10 decimeter cube flask or vessel. At equilibrium, 1 mole of carbon monoxide remained. Calculate Kc. And there's the equation. So initial is 2 of that and 5 of that, no CoCl2. At equilibrium, 1 mole of carbon monoxide remained, so we've got 1 mole left. Remember, these are the moles. So the change is obviously a drop of 1 mole. Started with 2, got 1 at equilibrium, so we've lost 1. The mole ratio between these two is 1 to 1, so this will also lose 1 mole and go to 4. 1 to 1 still, so this will go up by 1 mole, and so we will have 1 mole at equilibrium. Equilibrium concentrations will be the moles divided by the volume, so 1 over 10, 4 over 10, 1 over 10, so that's 0.1, 0.4, 0.1. There's the expression for Kc. Equilibrium concentration of CoCl2 divided by the CO concentration multiplied by Cl2 concentration. So we'll feed in the equilibrium concentrations, 0.1 divided by 0.1 times 0.4, and that comes out at 2.5. The units would be, we've got 1 lot of moles per decimeter cubed on the top, but we've got 2 on the bottom, so effectively the units on the top would cancel with 1 of the units on the bottom, so we'll be left with 1 over moles per decimeter cubed, so that will become dm to the plus 3 moles to the minus 1.